Back to the question we started at talking about last time, which is how to compute the similarity between two sequences, how to compute it efficiently. And what I did last time, remember, is I defined and described this thing called an alignment graph. And then we saw that there was a one-to-one correspondence between alignments of the two sequences displayed on the alignment graph and paths in the alignment graph from the upper left-hand corner to the lower right-hand corner. And that correspondence really going to help clarify our thinking about alignments and how to compute good ones. So I'm going to go back to pretty much where we stopped last time. Get the screen. Okay, so here's the alignment graph we were dealing with last time that aligns Dan and Ann. And what we said again was that every path from the upper left-hand corner to the lower right-hand corner in this alignment graph specifies an alignment, a unique alignment. Every two paths that are different specify different alignments. And conversely, every alignment corresponds to one such path, and two alignments that are different correspond to different alignments, different paths. And then we introduced this notion of weights or distances on the edges. So a distance of 1 meant that the edge that went into here corresponds to two characters that are the same. So this is a match. Here's another match. Here's another match. Or you can call it a potential match if it's used in an alignment. Every other edge that doesn't have an explicit weight on it is assumed to have a -1, which really means it's either a mismatch, like this one is, N opposite D, that's a mismatch, or it's a horizontal edge, which means it's a space that's being introduced in the alignment, or a vertical edge, which is also a space introduced into the alignment. So we ended up last time by saying if you can find the path from here to here with largest total sum, that path specifies the alignment that maximizes the objective function that we're interested in. Without writing it up on the blackboard again, it maximizes the number of matches minus the number of mismatches minus the number of spaces in the alignment. Okay, so then we got onto the question of how do I find that path, or a path, there may be ties, how do I find a path that has the largest total sum, or largest distance from here to here? Okay? And I started introducing this sort of procedure, which was, it follows the following idea. I really want to compute the longest path from here to here, and the way I'll do it is by computing the longest path from here to each of the other nodes in this alignment graph, ultimately finding the longest path from here to here. So we start with the really easy questions. The really easiest question, what's the longest path from here to itself? That's at length 0, and the path itself is just to sit there. Okay, you can't go anywhere and come back. That's just the way the arrows are pointing. And then another simple question is, what's the longest path from here to here? Again, there is only one. You're forced, and its distance is -1. That was what's written here. This -1 is not for this edge, but for this node. Then we ask, well, what's the longest path from here to here? And again, the only way to get to here is through there, through this node. And so it's -1, which is what it was to get to here, minus another 1, which is what happens along this edge. So the total to here is -2, and that's what's written here. Again, this -2 is for this node and not for that edge. All right, we continue. What's the longest path from here to here? What's the distance of that longest path? And again, the only way to get to here is through there. And we know that the longest distance to there is -2, and the distance along this edge is -1. So the longest distance to here is -3. Okay? So now I've figured out what the longest distance is to each of the nodes along the first row, or the 0 row, and I can do a similar thing along the 0 column. Okay, so those are the easy cases. Ultimately, remember, my goal is to figure out what the longest path is to each one of the nodes inside here, in particular that one. And what's the next easiest case? Once I've done these guys and these guys, well, it's this one. Because the way you reason is that to get to here, the only paths either go, the last node that is visited before I get there, either go through that one, and I know what that distance is, that's a -1. So if I take the path that goes through that one, that's -1 with another -1, which would make that way -2. That's one possibility. Or it's to go this way, because this is the last node visited before this one. This one is a 0 with a -1, so that possibility gives me a -1. Possibility coming through here is also -2. So the largest over those three possibilities, -2, -2, and -1, is, the largest is -1. It's easy to get confused and talk about and think about absolute value and say, no, the largest is -2. No, the largest is -1. So I now know what the distance is to here. It's -1. Okay? Now let's look at this one. This is a little bit more instructive to look at this guy. Again, the reasoning is going to be this. To get to here, the last node I visit, if I think of all the possible paths that take me from here to here, the last node I visit before this one is either this one, or this one. Three possible neighbors. That's important to keep in mind. If the path I take goes through here, then the distance is -2. That's the longest distance to get to here, with another -1, so that would be a -3. If it goes through here, then it's a -1 with another -1, that's a -2. And if it goes through here, it's a -1 with another -1, that's a -2. So you have three possibilities, -2, -2, and -3. The largest of those is -2. Okay? Let's just do one more before I make my main point. Let's try that one. What's the longest distance to there? Well, that path, the best path that gets to here, either goes through that node, in which case its distance is -3, -1, which is -4, or it goes through that node as the last node before it reaches there, which is a -2, -1, which is -3, or it goes through there, which is -2 with a -1, which is -3. So again, we have three possibilities, -3, -3, and -4. The largest of those is -3. Okay? Now the key thing I want to point out here, and it's true everywhere else, is that when I figured this out, after I had already done the three neighbors, I didn't have to, when I'm trying to figure out what's the longest path that gets me from here to there, I didn't have to think about all the possible paths. I didn't have to enumerate all the paths from here to there. Even though this is a small slice, there are a fair number of paths. We could figure out what it is, but it's certainly bigger than 3. Okay? I didn't enumerate all the paths that went from here to here and fully calculate all their distances. But what I did was only 3 kinds of operations. I said, whatever that path is that goes from here to here, whatever the best path is, in fact, any path that goes from here to here, the last node it visits before reaching here is either this one, but I already know what the largest distance is to there, so I would know that any path that goes through there before it reaches here has a distance of -4, or that path goes through here, in which case the largest distance that goes through here is -3, and similarly, it might have gone through here, in which case the largest is -3. Point being that when I'm focusing on this node, if I know already the longest distances to its neighbors, the amount of effort I'm making here is just basically looking at 3 pieces of information, 3 numbers, doing 3 additions, and then making a comparison between 3 numbers. So that's 9 operations or 8 operations, whatever you want however you count them carefully, it's just a handful of operations, okay? And it doesn't matter how many paths there actually are from here to here. The number of operations I do when I'm focusing on this node is just that 8 or 10, whatever that small number happens to be. Okay, let's just continue till we get down to here. What am I next ready to do in this picture? Which node is next ready to compute, or are there choices? I think there's only one node that we're ready to compute, whose distance we are ready to compute. Which one is it?
Third row, second.
It's what?
The third row, second one.
Sorry, what?
2, 3. I think 3, 2.
3, 2, 2.
3.
This one?
Yeah.
Okay, this one. All right. We're ready to compute the distance to here because we have the distances to its 3 neighbors, the 3 neighbors that point into it. That's the key thing. When you're looking at a node in the alignment graph, you're ready to compute the longest distance to it from this origin, provided you have the longest distance already computed to the 3 neighbors of that node, the 3 neighbors that point into it. Okay? So, looking at this node, the longest path to it either goes through here as a last node before it reaches that, in which case it would be -1, because that's the distance to there, with another -1. So -2 is a possibility. Or it goes through this node, in which case it's -1 with a +1, which makes this 0. Or it's -2, that's what this is, with another -1, which is -3. So we have 3 possibilities, -2, -3, and 0. The biggest of those is 0. So the distance to here is 0. Okay? And again, it took us just a handful of operations to calculate that. All right, now we're ready to look at this one, and it's either 0 with a -1, or -1 with a -1, -2, or -3. So I'm going to speed this up a little bit. This is a -1. Okay, it came from here. This one is, that would be a -2, -3, -4. So -2 is the best one there. And now we're ready to do the next row. Okay? So we have a 0 with a -1, or we have a -2 with a -1, or a -3 with a -1. So this is the best one, which is a -1. Now over here, we have a -1 with a -1, which is a -2, or we have a 0 with a 1, which makes it a 1. Or a -1 with a -1, which is -2. So actually now we're getting a positive value of 1. All right? And now to finish, where we actually wanted to end up, which is here, we look at those 3 possibilities. That's a -3, that's a 0, and that's a 0. So you end up with 0 as the longest, that's the sum of the longest path from here to there, according to these calculations. Now, hopefully, that's the same as what we got last time when we looked at different alignments. We saw that there was actually a 0, and we found actually that there were 2 alignments that did that, and we'll see that again in a little bit, how we learned that from this particular alignment graph. Okay? But does everybody see the idea? We're going to go row by row. You finish the top row. You can finish the first column, the side column if you like, first. And then you just proceed left to right in each row, and you always have the property that as you look at a new node, left to right, you're ready to compute its longest distance, the longest distance to it, because you've already computed the 3 neighbors of it. Okay, now, if people understand that, tell me, let me ask, is there some other way that I can organize these computations besides row by row that would work? Yeah.
Just grab that. But you go the first square, and it's the first one.
Mm-hmm. Okay, that would work, I think. Basically, the suggestion is, well, after I've done the top row and the side column, I get this one, which you can think of as doing that square. And then you could do this square. Well, yes, you can. I mean, you'd have to do this one for. You'd have to do these two before you got that one. Okay? But you can kind of think about going outwards in squares. You just have to come down a column and a row that way before you meet at the end. But I'm looking for something a little bit simpler, actually. We've said how you can go row by row. What else works? I see the hand motions, so I know the hands are connected to the brain, so the brains must be doing the right thing. So what's the answer? You can do it by column, okay? Actually, everything's symmetric here, really. You could just argue that, well, just flip over the picture, and what used to be a column is now a row, and why shouldn't it work? But again, you can really see it by arguing it. If I have let's say this row and this column, I'm ready for this one. That's what we did before. And after I do that, I'm ready for that one. And after I do that, I'm ready for that one. So that's going column by column. Okay? And there's actually another way of doing it that has some advantages, which is anti-diagonal. Okay? Which is, you do this one, then you do these two, and then you're ready to do these three, and then you're ready to do these four, and then you're ready to do these three and these two and this one. Okay, you can march that way too. The key thing is that however you organize it, you can't do a node until its three neighbors have been done. And that's the thing to keep in mind. Okay, now I'm going to come back to this picture in a little bit, but I want to turn on the lights to do a little bit of board work, and I've been told if I don't turn the lights on and this off, then the video ultimately is not of good quality. So what is the point? Of this approach? Computing similarity. Of two sequences of lengths n and m. Why are we doing this? Why did I just go through that method? What are we trying to achieve? I thought I heard somebody say an answer. Yeah. Well, find an algorithm. Yes, you definitely want something that's concrete and has a clear description, a clear, precise description, an algorithm. But what specifically? I mean, we really had, in a sense, an algorithm before. The algorithm was to enumerate all possible alignments. And I even sort of sketched out how you could write that in 3 loops. But what was wrong with that approach was that there are just too many alignments. I showed you a formula. If you plug in n, I assume both at that time there were both sequences were length n. If you plug in n, you get a number. Let's say for n equals even 100 probably. which has more alignments probably than the number of electrons in the universe, whatever that means. People always say that kind of stuff. Anyway, it's clearly huge, just so huge that it's impossible to enumerate them all. So we're looking for something that is vastly more efficient. And that's what I'm getting at here. We need something that's efficient as a function of n and m. And so now I want to do that analysis with your help. Analysis of the number of operations this approach uses. Okay, to do that, we think about it in the following way. For each node in the alignment graph, there's some amount of work that we had to do. We had to look at the distances for the neighboring nodes, look them up in some table. But everything ultimately is going to be organized in an array. I mean, I assume everybody here is programmed a little bit, so you can talk in that terminology, even though we haven't learned about arrays yet in Perl. You've learned about them somewhere. So if I'm looking at node in position ij, I need to know what the distance is in position I minus 1, j minus 1. I need to know what the distance is in position I, j minus 1. And I need to know what the distance is in I minus 1j. So that's 3 lookups in some array. Okay? 3 lookups per node. Then what do I do with each one of these distances? According to what is written on the edge, on the appropriate edge from that node to node ij, I do either I subtract one or I add one. That's it, really, right? So we have 3 additions. Additions in a generalized sense. One might actually be a subtraction. So, some would be subtractions. And then I have to figure out which was the largest of those 3 numbers. Okay? If I have 3 numbers, I can figure out the largest by doing 2 comparisons. Right, well, this is all small change. Let's just say 3 comparisons. Okay? So, anybody want to add anything else I have to do in there? Actually, I guess when I'm looking along an edge, I have to figure out what number was associated with that edge, whether it was a negative one or not. Okay, so some more lookups. Let's say 6. All right? Whatever you like. The fact, this is going to be some finite and relatively small number. And it's just not going to matter whether it, in the end, I call it 12 or I call it 20. But at the moment, let's just call it 12. So what I'm saying is that it's 12 operations per node. Okay? So 12 or so operations per node. And the key point is it doesn't matter how many nodes there are in the alignment graph. This could have been a 1,000 by 1,000 graph, and it's still, at any interior node in that graph, you're still just doing 12 operations. The number of operations per node does not grow as the size of the graph grows. Okay? 12 operations per node, no matter what n and m are. Okay? And that's key to efficiency. So now what I want to know is how many total operations. If we're doing 12 operations per node, to get the total number of operations, I simply have to know what? How many nodes there are. And how many nodes are there? Is what? About n times m. Actually, with the 0 row and the 0 column, it's n plus 1 times m plus 1. But n and m are the variables. That's what grows as the sequences grow. 1 is a constant. It doesn't grow when n grows. Okay? So we're just going to say this is about n times m. That's the number of cells or nodes. And then if the number of operations per cell is about 12, so this is about 12 nm. The key thing is that the number of operations grows proportional to the product of the two lengths. So certainly it's true that as the sequences get bigger, you're going to do more work. It's going to take longer to do this computation. But the growth is not explosive. It's relatively modest. So in fact, if n was equal to m, for n equal m, the total is about, grows proportional to n squared. Okay? Just if m equals n, then this is n squared. So the total is about, total grows, total number of operations is proportional to n squared, and therefore the time that the method takes, time needed, grows proportional to n squared. Now, how does n squared compare to the total number of alignments? We didn't do a full analysis, but I said the total number of alignments grows exponentially in n. Is this exponential? No, this is polynomial. This grows rapidly enough to be a problem at some point. And we'll get to that later. But for most ranges of n, this is not so bad. If n is 1,000, for example, 1,000 squared is only 1,000,000. What's 1,000,000 operations, or even 12 million operations on a computer today? You know, I think it's under a second. Okay, it's almost nothing. But exponential is something like, I'll just simplify it, 2 to the n. Okay? And actually, the analysis I wrote up in the notes shows that the number of alignments grows faster than 2 to the n. This is actually kind of a conservative estimate. And what's 2 to 1,000? Is that a big number? What's 2 to 64? You don't know off the top of your head? No, because 2 to the 64 is 8 by 8. That's a chessboard, right? So there is a story about somebody who has to put 1 grain of rice on the first square, 2 on the next one, 4 on the next one, 8 on the next one, doubling each time. That's only 2 to the 64, but it's more grains of rice than there are in the world. You know, if 2 to the 64 isn't, 2 to the 1,000 definitely is. And 1,000 is even still a small number, by the way. We want to do alignments with billions. Okay? Now, billion squared is going to be a problem. But 1,000 squared, 10,000 squared, that's no problem. 2 to the 1,000 is a problem. 2 to the 10,000 is a problem. So that's why we're going to all this trouble to come up with this other method besides the straightforward one that you can think of immediately, because it's just not practical to enumerate all of the alignments. But the method we just developed, you can compute the similarity value just with n-squared type operations. Now, I'm going to formalize this whole thing. I may even start today, but if not, next time. Formalize this a little bit, but what you've just seen is an example of what's called dynamic programming. So dynamic programming is a technique, is an approach to finding efficient algorithms that's used all throughout bioinformatics. And the point of using it is to get around this inefficiency problem, to find something that's relatively efficient, which means it'll work. Okay? And concern about this issue is why this class is in computer science, probably, and not, if this was in the biology department, we would just say, here's a tool, and you wouldn't know what thoughts went into making it efficient, or that there even was a problem in efficiency. But here we're addressing it directly. And it goes back to what I said, one of the first lectures was that although most people think of computers as being fast and having huge memory and having very smart primitive operations, that's the wrong viewpoint. The right viewpoint is that computers have small memories, and that becomes a problem. They're very slow, and that becomes a problem because you can't do brute force things of this magnitude. And they're really stupid. Probably everybody here knows that already, if you ever had to do anything with a computer. But by that I really mean you have to ultimately think about solving your problems on a computer in terms of very primitive operations. Looking at a cell, looking at some number, doing some simple arithmetic, and then moving on. That's often what you have to think about. Okay, so now I want to introduce the following problem. The method I've shown you computes the similarity value, 0 in the case of Dan and Ann. How do you get the actual alignment, the alignment whose value is 0? Where do we get that out of this computation? So now I'm going to go back to the overheads and talk about that. All right. Yeah, thank you. Great, that's good. Thank you. We did our computation of the numbers row by row, or you could do it column by column. And now we know that the distance between Dan and Ann, or the similarity value between those two sequences, has value 0. We also know from last lecture how to associate a particular path with an alignment. But what path is it, or which paths are there from here to here that have distance 0? And how do we find it? Well, this is the most subtle point about dynamic programming that most people have trouble with. Most people would like to think, and you should certainly try to make this work and discover for yourself why it doesn't, that you can somehow keep track of the path we want to use while you're going forwards, while you're filling in the numbers. So people would like to think that as I'm going forward, I'll just keep track of the best path. And when I get to here, I'll know what the best path was. The problem with that is that as you're proceeding along the initial portions of this, you may keep track of the path that gives you the largest number so far, but that path may die out as the best later on. It may not, in the end, be the winner when you get down to here. And meanwhile, you hadn't been keeping track of the initial portion of something which ultimately was going to become the best path. Okay, and the alternative is to somehow keep track of all the paths, but then we're back to this problem of enumerating the fact that there are too many paths. So what you do in dynamic programming, after we've computed the distance to here, you kind of work backwards from here back to here with a kind of reverse logic, which will tell you what is the path, or what is a path that goes from here to here with distance 0, or equivalently from here to here with distance 0. Okay, too many words. Let me tell you let me do this example, and then hopefully you get the idea, and then I'll write it up, and that'll hopefully be overkill at that point, because you'll all understand what I'm talking about already. So I know that the distance to here from here is 0. I've recorded that. Okay? And I know what the distances are to its neighbors. So I can say, I know there's a path from here to here that gets me there with total distance. What's the last edge on that path? Or what edges are possible as the last edges on that path? Well, I just sort of do a reverse kind of logic to what I did in getting these numbers. I say, well, I know this is a 0. This neighbor was a 1, and the edge along here is a -1. So that's not the right edge, because that would have given me a minus. Oops, that is the right edge, because that would give me a 0, right? So I mark that. I might do it for the other neighbors because there could be ties. I say this is a 0, this is a -1, and there's a 1 in between. So yeah, actually that would work too. If you think about it, what I've just said is I know for sure there is a path that goes from here to here with total distance 0 and uses this as the last edge. There's also another path that goes from here to here with distance 0 and uses that as the last edge. We're just thinking backwards from what we did. Now I can try this one as well. This is 0, this is -2, this is a -1. There's no path from here to here with total distance 0 that would use this as the last edge. Because the best way to here is -2, and this is a -1, so no way. You're just thinking backwards. That's all you're doing in order to find these paths. So let's proceed. Let's continue. And if I only want one path, by the way, I don't have to record ties if there are ties. Okay? So let's just look at this node. I know there's a path from here to here that has distance 1. If I can just find the last edge on that path, I can keep going. So is it this one? Well, that would be -1 with a -1. That's -2. No good. Here, 0 plus 1 gives me 1. So that is good. Okay? This would be -1 with a -1. That's -2. That's no good. So I go back to here. I know there's a way of getting from here to here with total distance 0. What's a last edge on a path that does that? Not that one. -1, -1, that one works. Not that one. Here. There's a way of getting from here to here with -1. What edge is it? That one. And there I have a path whose total distance is 0. Now, if you want, you can explore the other way. There was a choice here. And by the way, I actually did look at all the choices from these nodes. Those were all forced. There were no choices there. Well, from here, this is a -1. Okay? If I came from there, that would give me a -1. If I came from there, that would give me a -2. That would give me a -3, so it's got to be that one. And now, by the way, we're back to where we already looked at. So here's another complete path. And that's it. Those are the only two paths that give me a total distance of 0. I know that because I explored all the ties out of here. Everything that, wherever there was a tie, I did do a green mark. Okay? And now, because we know how to associate paths with alignments, you can actually write down what that alignment is. Or as you're going backwards, you can accumulate the alignment right to left. okay, instead of left to right. So that part of dynamic programming is called the backtrack or the traceback. So in dynamic programming, there's always two phases. One is the forward computations of numbers, and then which tells you the value of the alignment or whatever else you're computing. And then there's a traceback phase where you actually find the alignment or the actual solution that you're looking for. It's not just a number, it's some description, maybe just a number in some problems, but many times it's some other description of what a solution is. In this case, it's an actual alignment. Now, there's one subtle point, maybe. If I have ties, as I did here, how do I know for sure? Let's say I ignore this one, and I just say, okay, I'm going to go that way. How do I know for sure that there will ultimately be a path of distance 0 going that way? I mean, this is a question that usually comes up. How do I know I don't have to explore all ties when they're ties? And the answer, again, is just the logic. Think of the logic of the dynamic programming computations going forward. You know for sure that the distance to here is 1. The longest distance to here is 1. And this edge, that 1 plus a minus 1 is 0. So you know for sure that if you can find a path that has distance 1 to here, from here to here, distance 1, then this edge will be on some longest path, some path of length 0. And how do you know that you can find a path of distance 1 from here? Well, again, one of its neighbors had a value which is associated with the edge, the specific edges, gave it that 1. So what I'm saying is that the invariant property that's true as you're going forward is that whatever value you write at a node, there really is a path to that node from here that has that distance. Okay? And so whenever you can figure out what the last edge was on that path, you can just repeat that logic over and over again until you hit this one. And you will eventually hit that because all roads lead to Rome. That's where they're all going, back up there where they started from. Okay, if that didn't make a lot of sense, think about it at home. This backtracking is the most subtle part of dynamic programming. People, in my experience, for weeks afterwards keep coming up and saying, tell me again why I can't just compute it going forwards. I'm just going to keep track of whatever the best was as I go forwards. And that doesn't work. Now, I have 5 more minutes. There is an idea that's kind of halfway there. The breadcrumb idea. So as you're going forwards, there is something you can do, and it may be actually implemented in the Perl that I have for this. So I should tell you about it, which is to leave breadcrumbs or pointers from every node. So you say, now imagine I'm going forwards, doing my forward computation, and I give a value, I get a value for this node. I say, where did that value come from? Okay? That value, remember, was either 0 with a minus 1, or it was minus 1 with a minus 1, or it was minus 1 with a minus 1. So this best value here came from a path that used this as the last edge. So I could mark that. Okay? And I could do that for each one of the nodes that I visit. I could mark an incoming edge as the edge that was the last edge on a path that gave that node its value. And then when I finally finish down here, I can just backtrack along any one of those pointers or breadcrumbs. What's going to happen is that, let's say this node, nobody's going to end up pointing back to it. ultimately, a path that doesn't go from here back to there with pointers, any other path is just going to die out somewhere. So the backtrack is just as easy, maybe even easier, because you're not having to do the reverse logic. You're just following pointers that you already put there. In a way, all I'm saying is that where I was thinking backwards here and putting these green marks, I could be putting those green marks as we go forwards. And then whenever you follow green marks going backwards, it will bring you back to here. Even though there's lots of other green marks in this, there would be lots of other green marks in this alignment graph. Most of them will not lead to a path that ends up here, and therefore on the traceback, they'll be irrelevant. Okay? So let's see if, hopefully that makes some sense. Now, this is all pictorial. This is, I think, helpful in getting the idea of dynamic programming in your heads. Ultimately, we have to think about dynamic programming in notational terms for several reasons. So what I'm going to do, ultimately, and not today, is, in a sense, go over this whole thing again, not with a picture, but with mathematical notation. Well, let me leave you with one question before I do that. We learned about substitution matrices. Substitution matrices give different values for different kinds of mismatches, and even give different values for different matches. Okay? So now imagine I have the problem of aligning two sequences, Ann and Dan, but I have a substitution matrix. Right? It's not just that I'm going to get a 1 for each match and a -1 for each mismatch and a -1 for each space. Let's say I get a -1 for each space, okay? But what I get from each mismatch and what I get from each match is going to depend on what the characters are. All right? And again, of course, I want to enumerate. I don't want to enumerate. I want to compute efficiently. How do I change what I just showed you here to solve the problem of finding the best alignment, the alignment that maximizes the value of the matches minus the value what you get from the substitution matrix of the mismatches minus the number of spaces? Can anybody see the answer right now? And how many people are going to see this answer by Monday? You should all raise your hands, and you should all come up with the answer by Monday. It's very simple once you get this understood. All right, I'll see you on Monday.